This is the second part of Inverse Trigonometric Functions lecture. We'll talk about the remaining three functions, inverse to cotangent, secant, and cosecant. Let's recall the shape of cotangent function. We have a decreasing wave like this, and this wave repeats itself every pi. Since we have this repetition, as usual, we need to restrict the domain of cotangent to a certain one-to-one section in order for the inverse to be a function. So the domain that we want to restrict cotangent to will be 0 to pi. And in order to obtain the graph of arc cotangent, we need to reflect this part of the graph in the diagonal. This reflection will result in this shape. It's a decreasing function, and as you see, the domain of the inverse cotangent function is all real numbers, and the range is from 0 to pi. So the formal definition of arc cotangent is as follows. Arc cotangent of x is such an angle y that cotangent of this y gives us back the input x. The input x can be taken from any real number. That's the domain for arc cotangent, all real numbers. However, the output is an angle between 0 and pi. So that's the range between 0 and pi. Notice that since cotangent of y is x, and cotangent is 1 over tangent, therefore we can translate this equation equivalently into tangent of y is 1 over x. Because if we have equation 1 over tangent y equals x, then we can just interchange x with tangent y, and then tangent y would be 1 over x. So this conversion may be useful when you use a calculator and there is no cotangent button, so every calculation must be done in terms of tangent. If we use this conversion, then we can define the inverse cotangent function through the inverse tangent function in the following way. Inverse cotangent of x is the same as inverse tangent of 1 over x. But, well, we have to be careful about the domain. This formula works only for x is positive. Why it is so? Well, let's recall the tangent function. It looks like this, where here's pi half, and over there negative pi half. So that was the restricted domain of tangent, since the range of inverse tangent that looks like this is between negative pi half and pi half, then for x positive, the inverse tangent falls into first quadrant. That means the range of this expression is from 0 to pi half. However, for negative x's, this section of the restricted domain will fall into the fourth quadrant, which is from negative pi half to 0. So the values will be the same, but actually shifted to different quadrants. That's why to match cotangent, which is defined to be in the first and second quadrant, we need to add pi to it. So the second branch of this definition will be arctangent of 1 over x, but then plus pi if we use negative x's. And also arccotangent of x can't be defined through arctangent of 1 over x if x is 0. So we have to fill in this point. For x equals 0, arccotangent is equal pi half. So that's why we plug it in the value pi half. Because of this problem with shifting by pi, in some of the textbooks you will find that the restricted domain of arccotangent is actually taken from negative pi half without 0 till pi half. So that's another option of picking a section of cotangent and reversing it to the shape like this. That's negative pi half, and that's pi half. So you may see in various textbooks different definition of the restricted section of cotangent and arccotangent function. So the definition of arccotangent in terms of arctangent really depends on which definition of arccotangent we'll take. If it is as in our textbook, then this formula would work. If it is as I showed you here, then it's enough to say arccotangent of x is the same as arctangent of 1 over x. However, don't worry about this too much. Most often we are going to use just this conversion, and looking at the graph, we are going to move the angle in the proper quadrant. That means in the quadrant 1 or 2 for arccotangent. Okay, let's list the properties of arccotangent as shown here. The domain of arccotangent is all real numbers. The range is from 0 to pi. Asymptotes, they happen at 0 and at pi. So y equals 0 and y equals pi. The next function is arcsecant. So let's recall the secant shape. Normally it was like this, and the repetition every 2 pi. Again, we need to pick a section of secant that is 1 to 1, and the section that is suggested by our textbook is from 0 to pi, except for pi half. So here's the restricted domain. And then we are reversing this by using symmetry in the diagonal. After the symmetry, we obtain the graph like this. So there are two branches. As you see, the domain for the arcsecant is from -infinity up to -1. Then skip this section between -1 and 1 and go from 1 to infinity with the endpoints. The range is from 0 to pi half. Skip the pi half and continue till pi. And here we have the formal definition. As usual, arcsecant of x is such an angle y that secant of y gives you back the input x. Input x is taken from -infinity up to -1 or 1 to infinity, and the output sits in the interval from 0 to pi except for the point pi half. Similarly as for tangent, since secant y is x and secant is 1 over cosine y, then we can interchange x with cosine y, and we have equivalent form cosine y equals 1 over x. Since this is true, therefore the inverse of secant can be defined as inverse of cosine, but of 1 over x. And in this case, the restricted domain of arcsecant and cosine actually agree. Therefore, we have no problem like with arccotangent before. So the sections go into the right places. So that could be very useful when trying to evaluate arcsecant on the calculator, which doesn't have this button. Okay, let's list the properties of arcsecant function. The domain is the green section, so it's from -infinity up to -1, including, plus from 1 to infinity. The range is the red section, so it's from 0 to pi half. We skip the pi half and then continue towards pi with pi. And we have one asymptote. It happens exactly at pi half, so y equals pi half. And the last of our inverse trig functions are cosecant. Arccosecant is the inverse of cosecant, and the section of cosecant that we are taking to reverse is from -pi half, skip the 0, till pi half. Again, two branches. So the image of these two branches in the diagonal is as on this diagram. The domain for arccosecant is the same as for arcsecant, from -infinity to -1 and from 1 to infinity. However, the range is different. The range of arccosecant is from -pi half, skip the 0, till pi half. Let's look at the formal definition of cosecant. Cosecant of x is such an angle y that cosecant of y gives us back the input x. The input is taken from all real numbers except for the segment from -1 to 1, And the output is, as we said, from negative pi half till pi half except for 0. Similarly as before, cosecant of y equals x can be translated into sine of y equals 1 over x, because cosecant is 1 over sine. So again, we just interchange the x and sine y to get this equation. Therefore, the inverse cosecant can be found by just using inverse sine, but of reciprocal of the input of 1 over x. And you can notice that in this case, similarly as with arcsecant, the restricted domain of sine is in the fourth and the first quadrant, which is exactly the same as the restricted domain of cosecant, the fourth and the first quadrant. So there is no problem here with shifting the branches. And let's list the properties of our cosecant function. The domain, as we said, is from negative infinity till negative 1, union from 1 to infinity. The range is the red section, so it's from negative pi half to 0, skip the 0, and then go to pi half. We also have one asymptote, and this asymptote is just y equals 0. So that's the graph of cosecant function. Okay, so let's make use of the properties that we learned. We need to evaluate the expression by giving an exact value if possible, and if not possible, then by calculator. So first example is find arc cosecant of 2. Remember that any arc function gives you an angle. So let's call this angle theta and translate this into a regular function. So this is theta if and only if cosecant of theta is equal to 2. Well, cosecant is 1 over sine, so that's the same as sine of theta is equal to 1/2. We know that sine of theta is 1/2 for angle pi 6 for this angle. So our angle theta is pi 6, and that's the value for arc cosecant of 2. Since pi 6 is in the first quadrant, everything looks okay. The second question, arc cotangent of root 3. Again, let's assume this is certain angle theta and rewrite this in terms of just cotangent. This is such angle theta that cotangent of this angle is equal root 3. But that means that tangent of theta is 1 over root 3. Let's look at our diagram. 1 over root 3 is tangent of pi 6 again. Therefore, the theta by itself is pi 6. And it falls into first quadrant, so yes, we are in the range of our cotangent, so everything is fine. In the last example, well, that doesn't look like any special number. Therefore, let's rewrite this in angle theta and use calculator. But first we need to translate into something that is doable on the calculator. So this equation is equivalent to say that secant of theta is equal to negative 1.5. But secant is 1 over cosine, therefore that's equivalent to saying cosine of theta is reciprocal of this number. Well, negative 1.5 is like negative 3/2, so the reciprocal is negative 2/3. And then we use just inverse cosine of negative 2/3, which gives us theta equals cos to the minus 1 of negative 2/3. From the calculator is approximately 2.3 to 1 place value. In the next exercise, we have a triangle with the unknown angle alpha, one side 4, and the opposite side unknown x. Express alpha as a function of x. So we need to connect alpha with x. How can we do that? Well, the ratio of x over 4 gives us tangent of alpha. But we need to express alpha as a function of x, so we need to solve for alpha. How can we do that? Just by using inverse function. So if we apply inverse tangent to both sides of this equation, we'll end up with alpha from this side, and on that side we'll have tangent to the minus 1 of x fourth. So that's the expression in terms of x only. Therefore, alpha is a function of x as desired. The next exercise asks us to rewrite the expression in terms of x. So basically simplify this as much as possible. Let's look at the inner bracket. The arcsecant of x is such an angle theta that secant of theta is equal to x. That translates into cosine of theta equals 1 over x. Okay, great. But what's our expression? Our expression is actually cosine of theta, because that's theta. Okay, therefore this is just 1 over x. So the whole expression was simplified to 1 over x. Let's try this second example. Secant to the negative 1 of x is such an angle theta that secant of theta is equal to x. As before, that translates into cosine of theta equals 1 over x. Well, now let's draw a modeling triangle, because what we actually need to find out is what's sine of theta, not cosine of theta. So if theta is here and cosine is 1 over x, then the adjacent would be 1 and the hypotenuse x. Now to figure out what sine of theta is, I need this side. That can be found from Pythagorean equation. This will be square root of x squared, the hypotenuse square, minus 1 square, which is just 1. So sine of secant to the negative 1 of x is the same as sine of our angle theta, which is, from the modeling triangle, root of x squared minus 1 over x. Okay, so we have a general expression, but there is one more danger here. Well, we need to observe the sign of sine. Is it positive or negative? And we have a little hint here. Since the range of arcsecant is from 0 to pi, except for pi half, then sine of arcsecant of anything is always bigger equal 0. However, this expression, the numerator is bigger equal 0, but denominator, who knows? X could be either positive or negative. So what we really need to do is to put absolute value here to protect from becoming negative. Well, in the next exercise, we need to evaluate sine of 2 times arc cosine of something. Well, remember that arc function represents an angle. Let's call this angle theta. So we really have a situation sine of 2 theta. Now let's apply the double angle formula. That's the same as 2 sine theta cosine theta. Okay, so let's look closer at what the theta is. What kind of angle is that? This is such an angle that cosine theta is equal root 3 over 2, which means it comes from special triangle 1, 2, root 3. So root 3 over 2 is cosine of this angle, and that angle is pi 6. Therefore theta is pi 6, and we can complete the calculation. So it's 2 times sine of pi 6 and cosine of pi 6. Sine of pi 6 is 1/2, so it's 2 times 1/2, and cosine is root 3 over 2. So altogether we end up with just root 3 over 2. Now we want to solve equation tangent of something is pi quarter. Solve it for x. Okay, since tangent of something is pi quarter, then if we apply arctangent on both sides, it will cancel the tangent, and we end up with x plus root 2 over 2 equals arctangent of pi quarter. So arctangent of pi quarter is some angle that can be approximated from calculator. The approximation is about 0.6658, but we're not going to use this approximation. This is just for our curiosity. Now, to solve for x, we give the exact value by just using arctangent of pi quarter and then minus root 2 over 2. So that will be the solution in the first period of tangent. But if we want the overall solution, then remember that we can always add any multiple of pi because tangent is periodic with period pi. So the overall solution will be plus any k pi, where k is an integer. So those are all solutions. The solution is first period, is just this first number, and then you can add any multiple of pi to produce infinitely many solutions to this equation. Obviously, if we're curious what's approximately tangent to the minus 1 of pi quarter minus root 2 over 2, we just use our calculators and we end up with approximately negative 0.0413. But this is the root only in the first period, and then we can add any multiple of periods to produce infinitely many roots. In the next example, we are asked to solve for y in terms of x. Well, let's bring the 3 to the other side first, so multiply by 3. Then we are closer to y under arc sine. Now we need to get rid of arc sine, so we apply sine to both sides of the equation. Therefore, sine of 3x plus 1 equals 5y. And finally, y equals 1/5 of sine of 3x plus 1. And in the following example, we want to verify the identity for x bigger than 1. The fact that x is bigger than 1 protects the radicand. The radicand is positive and the denominator is not 0, so this is well defined. Well, let's see what the left-hand side of this expression is. Again, let's call arc cosecant of x an angle theta. Therefore, cosecant of theta is equal to x, which means that sine of theta is equal 1 over x. And our standard modeling triangle will look like this. If this is theta, sine of it is 1 over x. Therefore, the third side of the triangle from Pythagorean equation is x squared minus 1. Since x is bigger than 1, this is well defined, and we can state what tangent of theta is. So, tangent theta is 1 over root of x squared minus 1. Oh, that's great, we are nearly there. The only thing that we still need to do is get rid of irrationality. That means multiply by x squared minus 1 here and there. And yes, indeed, the left-hand side is equal to root of x squared minus 1 over x squared minus 1. So we have the right side starting from the left side. Therefore, the identity is proven. We've been talking about inverse trig functions and their basic graphs. Now we can apply the techniques of various transformations of the basic graphs of inverse trig functions. For example, we want to graph arctangent of x plus 1 minus 2 without a calculator. So the idea is to recall the shape of arctangent first. Let's say if this is negative pi half, and that's pi half. arctangent looks like this. We have asymptotes here. It comes through 0, 0, 1 pi quarter, and -1, -pi quarter. So these 3 points are kept. Great, that's the basic arctangent function. Now to graph f of x, what we need to do is apply translation by the vector opposite to whatever you see inside and the same sign outside. Translation by the vector -1, -2. So the asymptotes will be moved -1, -2. So the new asymptote is actually here. And that asymptote again, -2, is over there. So this number is -pi, and that number is 0. The main points, these 3 points, will be moved 1 to the left and 2 down, this one as well, and that one as well. So those are the 3 main points, and we volunteer a shape. So the red graph is the graph of f of x. And the last question is some application problem. Use the diagram to determine the values of x for which theta is 10 degrees. Theta is this small angle. It's the difference between alpha and beta. And the x is the horizontal distance from the camera to the diver. Okay, so what do we know? We know that alpha minus beta is our theta, and that's 10 degrees. We know the height at which the diver stands, and we know the height of the diver. So that's our theta. And then how can we connect alpha with x? Well, we can look at this big right angle triangle and just 18 plus 8, which is 26, over x, that's tangent of alpha. Similarly, using the smaller triangle, 18 over x, it's tangent of beta. To follow this equation, let's solve for alpha and beta by using arctan functions. So, alpha is the same as arctan of 26 over x, and beta is the same as arctan of 18 over x. Since alpha minus beta is 10, we can make equation tangent to the -1 of 26 over x minus beta, which is tangent to the -1 of 18 over x. This is equal to 10, or rather we can subtract 10 and make it equal to 0. So that's 10 degrees. Now we need to find the x's that will satisfy this equation, meaning if I create a function f of x out of the left-hand side of the equation, then I can just plug it in this function to the calculator and investigate zeros. So please plug it in f of x to your calculators. I would suggest that you use the following window, 0 to 40, and y coordinates from, let's say, -5 to 5. Find out zeros of this function just by using second calc function zeros. There will be 2 zeros. The graph will look somehow like this, and we will be after these 2 zeros. Those are the x's that we need. So please calculate this on your own. You already know how to use your graphing calculator. The zeros should be approximately 1586 and 2951 feet. So we have 2 points, 2 instances, when the angle theta is exactly 10 degrees. X could be close to 16 feet and close to 30 feet. Both instances will result in the same angle, 10 degrees. Now, what value of x will maximize theta? Well, this time we're after maximizing the function that represents just angle theta, so let's call it theta of x, which is nearly the same except for this minus 10 degrees. So we'll maximize tangent to the -1 of 26 over x minus tangent to the -1 of 18 over x. So you may want to plug it in this function again to your calculator and then use the window that will extend the y coordinate maybe to 15. So you may want to use this window, -5 to 15, just because this function goes 10 higher than the previous one. Or you can even use the same function and use the second calc maximum feature of your calculator, because the maximum of this function or maximum of that function will happen at the same angle theta. So if this is f of x, the theta of x has the same shape, but it's just shifted 10 units up. So the maximum will be at the same moment. And if you calculate your maximum, it should turn out to be approximately 21.63 feet. So this is the application of trigonometry and technology. So this tells us that at 21.6 feet, the camera will have the biggest angle, so it will catch the most. One more remark here. Make sure that your calculator is in mode of degrees, otherwise you may have a problem to see the graph. So I hope you've got the roots and the maximum, and enjoy the question.